Okay, let's do some math for fun. Today, I would like to introduce you guys the Chebyshev Polynomial, and we'll also be solving a very nice Quintic equation, so have a look right here. Well, the motivation of this right here is actually from trig, in particular cosine. So let's take a look at cosine of 2 theta. And of course, this is just the double angle identity for cosine. We can write this down as 2 cosine squared theta minus 1. And as you can see, when we have cosine of 2 theta, on the right hand side, we have a second degree right here, and we can actually look at this as a second degree polynomial in terms of cosine theta. And now, if you look at the triple angle identity for cosine, so let me write this down right here. This right here is actually equal to 4 cosine to the third power theta minus 3 cosine theta. Have a look. When we have 3 theta right here instead of the cosine, yes, we have a cubic polynomial in terms of cosine. And now the question is, what if we have cosine of 4 theta, 5 theta, and so on, so on, so on? Do we always get a polynomial in terms of cosine on the right hand side? And of course, you know the answer is yes, because otherwise, how can we continue with this video, right? Well, before I move on, let's actually go back, right? So let me show you guys cosine. This is the single angle identity. So let's look at cosine of 1 theta. Ladies and gentlemen, this right here is just equal to cosine theta. Wow. Now, you guys ready? Yes, we will be talking about cosine of no angle, the zero angle identity. Yes, 0 theta. And yes, this right here is just equal to 1, right? So, that's pretty good. Now, before we do the cosine of 4 theta, yes, you can just break it down as I say cosine of 2 theta plus 2 theta and then use the angle sum identity. Before we do that, let me actually talk about the general case. Here we go. A Chebyshev polynomial, in fact, is just, we are just looking at cosine of n theta. And this right here, it's going to be an nth degree polynomial, and the notation for that is just Tn. Why not C? I don't know. It's just Tn, that's the usual notation. And then the input is cosine theta. So that's how we write this down right here, right? A polynomial in terms of cosine theta, just like this right here. All right, now I want to see if there's any connection between the next one and maybe the current one or maybe the previous ones. I don't know. There's actually a very nice recursive formula. All right, so let's do a general case. Yeah. So let's take a look at cosine. Here we have 3 theta. I want to go to the next one. So let's consider n plus 1 theta. And let's see what we get from here. Well, of course, this is the same as saying cosine of n theta plus theta. And then based on this, we can use the angle sum identity for cosine, which is cosine of the first times cosine of the second. So let's write that down. So we have cosine n theta times cosine theta. And then when we have the angle sum, yes, this right here is a minus. I do have a proof for this, so go ahead and check it out if you would like. But anyway, this is a minus, and then we just do sine of first times the sine of the second. So this is what we have. Now, here's the deal. As you can see, to get to the next term, right, it's based on the previous terms. So that's pretty good. But we really want to have a expression with the Tn, because remember this right here, it's like saying cosine of n plus 1 theta, which is Tn plus 1, right? Okay, so I really want to make that happen, and this is how we can make that happen. Well, as you can see, earlier we said when we have the subtraction here, inside it's actually the addition, right? But if we have an addition here, in fact, it's going to be a subtraction. And this is how we can produce addition. Check this out. This is a common trick. What we do is we actually have to add this and then subtract this, and you'll see why. So if we add this, so I'm just going to put this down again, cosine of n theta times cosine theta. I'm just going to add this again, which is cosine n theta times cosine theta. But of course, we will have to subtract it so that we don't change the value of this expression. So let me put that down right here. And of course, don't forget to write this down. Minus sine of n theta times sine of theta. this and that, when we add, of course, we get 2 of them. So this is just equal to 2 cosine n theta times cosine theta. That's good. Now, minus, minus, we can factor out minus. So we can just look at this as a negative, right? And then we will have what? Yes, cosine of n theta times cosine of theta, and then this will be a plus, and we have sine of n theta times sine of theta. And you see, that's exactly what we want, right? And now, you might be wondering, how in the world do we know to add this guy and subtract this guy? Well, because I will show you guys the property, and what you can do is, if you know the recursive property, you can just take the result and then just work backwards, and you'll realize, hey, that's exactly what you do. So that's a secret. I'm not genius, all right? Anyway, finally, let me just put this down. We have 2, and this is, let me actually write this down first, right? So we have 2 cosine theta times cosine of n theta, and then all this, I will just write it as minus. Again, when we have the sum right here, in fact, what we do is cosine, and then we just do the first angle minus the second angle, right? The first angle minus the second angle, which we get n theta minus theta, factor out the theta, so we get n minus 1 times theta. Well, as you can see, if we write this down as Tn of cosine theta, so let me just put this down, Tn plus 1, and then again, the input is cosine theta. This, which is that, is going to be this, which is 2 cosine theta, and this guy is just Tn of cosine theta, so let's go ahead and put that down. And then this guy is just going to be, well, let's write down the minus, and this is just T sub n minus 1, and again, we have cosine theta. So ladies and gentlemen, this right here is the recursive formula when we are talking about the Chebyshev polynomial. And in fact, this is the Chebyshev polynomial of first kind when we are talking about cosine. And for the second kind, it's just that you talk about sine, right? I think cosine is neater, of course, so that's why we are focusing on this right here. All right, so definitely know this, and definitely know this. And I will actually use this to show you. In fact, you can prove this based on this recursive formula. Yes, you can also do complex analysis to get the angles, right? Use the Moravec's rule and all that, but Chebyshev is the deal today. All right, so just to demonstrate that this actually works, so let me erase this real quick, and I'm not going to look at my shirt anymore. Cosine 3 theta, which we are trying to get to the next term right here, right? What we have to do is, we first do 2 cosine theta, so let's go ahead and put that down, 2 cosine theta, and then we're going to multiply by the previous polynomial, which is just this, so I will multiply by 2 cosine squared theta minus 1, yeah? So that's that part. And then we are going to minus the previous part, because this is the next one, this is the current one, and this is like the previous. So it's a previous right here. So we have this, and then we are going to minus that, which is just another cosine theta. And ladies and gentlemen, have a look. This times this is going to be 4 cosine to the third power theta, and this times this is going to be minus 2 cosine theta, and then minus another one, so altogether we have minus 3 cosine theta, right? So yeah, I didn't really need to use my shirt, but why not? Well, as I told you, we will have a quintic polynomial. So yes, let's just go ahead and get to cosine of 5 theta. And in order to do so, we actually need this guy. So do the same thing. I'm going to have 2 cosine theta, and then we are just going to multiply by the previous one, which is this 4 cosine third power theta minus 3 cosine theta. And then we are going to minus the previous one, which is this one. So go ahead and minus. Here we have 2 cosine squared theta minus 1, like that. And now let's see what we have. Well, have a look. This times that is going to be 8. And then we have cosine to the 4th power theta. And seriously, this is really neat because again, when you have cosine of 4 theta, you get a quartic polynomial in terms of cosine theta. Really cool. Anyway though, this times that we will have negative 6 cosine square and then minus 2 more. So altogether we get negative 8 cosine square theta. And lastly, negative 1 is just going to be plus 1. So that's the identity, like the quadruple angle identity for cosine, which is really, really cool. Now, okay, we are going to get the 5th degree polynomial, right? So have a look right here. I'm going to leave it right here. How are you guys doing? Let me know. Yeah. All right. So now let's see. I have the cosine of 5 theta, and ladies and gentlemen, this is how we are going to produce a very nice quintic polynomial. All right. Right here, I need to do 2 cosine. So let's go ahead and put down 2 cosine theta. And then we are going to multiply by that guy, which is 8 cosine to the 4th power theta. And then minus 8 cosine square theta. And then plus 1, right? And then we are going to minus the previous, which is that guy. So minus, we have 4 cosine to the 3rd power theta minus 3 cosine theta, like that. So let's see what we have. This times that we have 16, and then we have cosine to the 5th power. Good. All right, then we have, how many 3rd powers do we have? This is 2 times negative 8, which is negative 16, and it's cosine 3rd power, but we have minus 4, right? So altogether we have minus 20 cosine to the 3rd power theta. And let's see, this is 2 cosine theta, and then minus become plus, so we have plus 5, and this is cosine theta, and that's to the 1st power. So, ladies and gentlemen, this is the cosine of 5 theta identity, just like that. Very cool, right? Now, here is a fun fact, and you guys can think about if this is true or not, and then, well, it's a fact, so it's of course true. I mean, go ahead and think about the proof of this fact. Right? If you add up all the coefficients of in the Chebyshev polynomial, you will always end up to be 1. So I'll just tell you guys the sum of the coefficients is equal to 1 when you have a Chebyshev polynomial, including the constant term, by the way. So let's just see, 16 minus 20 is minus 4, and then plus 5 is 1. Yes. 8 minus 8 is 0, and then plus 1 is 1. And then 4 minus 3 is 1. And then 2 minus 1 is 1. And then 1 is 1. 1 is 1. Yeah, this is a fact. But think about it, how you will prove this right here, right? So that's what we have. And let me just write this down right here for you guys nicely, and I will tell you guys how we can produce a very nice quintic equation that you actually know how to solve, that other people might not. Right? So let me just erase the board right here. And now to produce a very nice quintic equation from this identity, we can just do the following. Look at cosine 5 theta and pick a number from negative 1 to 1. But do not make it equal to negative 1 or do not make it equal to 1, because otherwise your quintic equation will only have 3 real solutions. So let's pick 1/2 and you'll see, and then our polynomial later on will be, with integer coefficients, all that stuff. So this is what we want. We want this, right? We want this to be equal to 1/2, right? And this right here, in fact, what we are doing is we are actually finding all the solutions first, and then we'll write the quintic equations. But we know the solutions right already, so it's really cool. This right here is so much cooler than give me 5 numbers such as 1, 2, 3, 4, 5, and then just do x minus 1 times x minus 2, and then no. This is so much better than this kind of approach to produce a quintic equation, right? All right, So this is what we want to end up with. We want this to end up with 1/2. Now the question is, cosine of what angle will give us 1/2? Well, let me give you guys a picture first. A reference triangle right here, right? We want to have 1/2. X is 1, and then the radius right here is 2. Well, as you can see, the reference angle here is just 60 degrees, which is pi/3. But we do have another reference triangle down here. This will also give us the same cosine value, right? So just keep that in mind, and this is still equal to 1. This angle is still the same as pi/3. And this is what we do. First, we are going to make phi theta equal to the first angle, which is pi/3. And let me tell you, we need to produce 4 more, because when we have a Quintic equation, we can have at most 5 real solutions, right? And as you can see, once we do all 5 right here, we actually have the solutions to the Quintic equation that we are about to get already. So the first angle is pi/3. What's the next one? Well, to keep it simple, I'm just going to rotate, right? So this is pi/3. I'm going to go from here to here. And as you can see, we just have to add 4 pi/3, which is going to give us 5 pi/3. So that's the next one. And then the next one, I will just have to go from here to here. So I have to add 2 pi/3. So that will give us 7 pi/3. And then I will just have to add 4 pi/3. So that will give us 11 pi/3. And then I will have to add 2 pi/3. So it's going to give us 13 pi/3. And the next one is going to be what? Yeah, plus 4 plus 2 plus 4 plus 2 plus 4. So it will be 17 pi/3. And yes, so on, so on, so on. But this right here, we don't need it. You will see why. Anyway, divide everybody by 5. So here you see we have pi/15, and then divided by 5. This is actually really nice. It's just pi/3. And then we have 7 pi/15, and then 11 pi/15, and then 13 pi/15, and then 17 pi/15, and so on, so on, so on. But remember, we want the cosine value at these angles. The truth is, cosine at this angle and cosine at this angle, they will be the same. So let me just write this down real quick. Cosine of 13 pi/15, this right here is actually equal to cosine of 17 pi/15. How do we know? Well, if you utilize the idea, you can see this right here right away. So 13 pi/15, let me just draw it right here. It's a little bit less than pi, so it's going to be like this. Well, I know, bad picture, but let me try again. So this right here is 13 pi/15. And you see, from here to here, we need 2 pi/15 to produce the whole pi. And then if we add 2 pi/15, that will give us 17 pi/15. So you see, if you look at the reference triangle, they have the same x values. So therefore, they have the same cosine value. Therefore, we can stop right here. The next one will be the duplication from one of the previous ones as well. So these are the 5 angles that we want. And now this is the final step. I'm going to write this down right here for you guys. Here we have 5 numbers already, namely cosine at these 5 angles. And I'm just going to call them to be x because I want to write my Quintic equation in terms of x after all, right? So the first number is cosine of pi/15, and please do not ask me to write this in terms of square roots. This is cosine of 12th degree. It's doable, but this video is pretty long already, right? So no. Anyway, we have this, and then next we have cosine of pi/3, and guess this is just what? 1/2. And then next we have cosine of 7 pi/15. And by the way, 7/15 is my birthday, so this is a very good number right here. And then we have 2 more, cosine of 11 pi/15. And then lastly, we have cosine of 13 pi/15. So we have these 5 numbers already. And by the way, they are pretty crazy if you look at their square root forms. But anyway though, we know that these numbers are solutions to the equation. Well, what equation are we talking about? Remember that when we plug in these values right here, solutions to the equation. Well, what equation are we talking about? Remember, when we plug in these angles right here, for this theta, we will end up with 1/2 right here, right? And on the right hand side, we have the cosine theta as like the building blocks of the polynomial. So in fact, I'm just going to write down the left hand side, it's just 1/2, right? And then when we see the cosine theta, we're just going to replace them with x. So right here, we get 16, and we get x to the 5th power, and then minus 20x to the 3rd power, and then plus 5x. And if you don't like to have a fraction in your Quintic equation, and if you don't like to have this equal to like 1/2 whatsoever, well, let's multiply everybody by 2, and then bring this to the other side. So ladies and gentlemen, right here I'll write down 32x to the 5th power minus 40x to the 3rd power plus 10. I almost got it wrong. If I got this wrong at the final step, I will cry. 2 times 5 is 10x, and then bring that to the other side, which is going to be minus 1. This right here is equal to 0. Congratulations, and this time I'm going to box this in red. So cool. These are the solutions to this Quintic equation. I guess I didn't really solve it, but I produced a very nice Quintic equation. And now, if you are wondering, how can we look at this and then figure out or solve this and get all this right here? Well, notice 1/2 is actually a solution to this equation. And after that, just good luck, because you will still be dealing with a quadratic equation. Yeah, but anyway, I think this is really cool. A lot of nice polynomials are actually from trig, and that's Chebyshev polynomial, right? Anyway, as always, that's it.